5 days, 4 nights. A lot of driving. I drove from,
Okay.
An hour.
This is being
I'm sorry.
recorded.
I drove.
All right, here we go.
Okay.
We're really gonna start now. So I am very happy to introduce Professor C.D. Hoyle from Cal Poly Humboldt.
Hmm.
I managed to train myself to say Cal Poly Humboldt, even though I can't say Humboldt. He got his bachelor's degree in physics from CU Boulder and his PhD from UW, and where he worked with Professor Eric Edelberger.
Hmm.
And then he did a postdoc at the University of Toronto, Italy, working on drag-free technology for the LISA Pathfinder mission. And then back at UW, working on Apollo lunar laser ranging. And then he came to Cal Poly at 2007, where he works on different laboratory scale tests of gravity, including measuring the big G and other things that he's going to talk to us about today too. And he's still involved in various projects like LISA, I would imagine, and working with.
A little bit, yeah.
And we'll get to hear all about that because he is going to talk to us about, is Newton's universal law of gravitation truly universal?
Yay.
Now,
All
I
right. Well, thanks, Lynn. Thanks, everybody. Sorry I couldn't be there in person, but this
all the people in the waiting room.
will work out. And yeah, I'm really happy to talk to you today, trying to give whatever support I can to your department in this time. So yeah, and I'm going to talk a little bit about, so I'm up here at Cal Poly, Humboldt, we're an undergraduate only institution, just like you. And I'm going to talk a little bit about the various projects I've been working on and how students have been involved with that and what we're kind of been doing and hope to get done in measuring gravity. If you want, I know it's not super easy in this kind of forum, but if you have a question, I don't mind taking them on the fly if you want to interrupt me somehow. Or if you want me to kind of backtrack, just let me know. And yeah, and so I'm going to talk, the work I'll talk about, it's been supported by NSF for a long time and more recently by NASA and then my collaborators in Italy at the INFN. So yeah, I'll just go ahead and get started. I have a fair amount of slides. So if it'll let me go forward, I will see here. Okay. So I think, from first year physics, we're all familiar with Newtonian law of universal gravitation. And what I mean by the title of this talk is, is this truly universal in the sense of, is it valid at all times and places in the universe? Is big G truly a constant throughout time? And does this work for example, does it matter what the masses M1 and M2 are made of, or does it just matter that they have mass? And does it matter who measures this distance, or, and what frame of reference should we measure R? Is G constant? What are these masses? Things like that. And it turns out there's a variety of laboratory experiments we can do. You might, when you think about measuring this law, you might think about, oh, we need planetary sized objects, right? But it turns out there's a fair amount we can do in the laboratory as well. And I'll talk about some of those precision measurements today. First, for example, is the force really inverse square? That's kind of assumed to be true down to very small distances, but that has not really been measured to be true for masses that are separated by very, very, very small distances, right? Is big G truly a constant? And if it is, what is its value? We'll talk about later that big G is the worst known fundamental constant in nature. And it's even been worse in recent years because there's been a lot of measurements that disagree on about its value. And lastly, when we look at this part of Newton's law, do we care what kind of material makes up these masses M1 and M2, or does Newton's law really just depend on the amount of mass? Okay, independent of kind of composition. And so the experiments we'll talk about. We have some torsion pendulum measurements of the inverse square law, which I'll abbreviate. You know, if you hear me say ISL, that means inverse square law, or is the 2, you know, in the exponent of Newton's law really 2? The weak equivalence principle, I'll talk a little bit more about what that means later on. We have efforts ongoing here at Cal Poly and through collaborations to kind of test these properties of Newton's law. There's another experiment where we're going to try to make the world's most precise measurement of big G. And something that's really new that we just got a NASA grant for in the last few months is working with actually a former student of mine, and Holly at NASA on developing new quantum sensors that we can use to measure tiny variations in gravitational fields. And so we'll be talking a little bit about all of that. And if there's any questions, you can let me know. Otherwise, I'll keep going. So let's just do a little recap here, and kind of the big picture. There are 4 known fundamental interactions, fundamental forces in nature, right? We have the strong nuclear force, we have the electromagnetic force, which we're familiar with, the weak nuclear force, and gravity. If we think about the range over which these forces act, well, gravity and electromagnetism are both infinite range, right? They both kind of behave as, you know, they're 1 over square and inverse square for gravity and for electrostatics, for example. The other 2 forces are, you know, only relevant over very small distance scales, right? Like kind of on atomic or nuclear distance scales, or like nuclear distance scales. And if we think about the strength, or in other words, you know, per unit charge, how much force do we get, right? The strong nuclear force is the strongest force. And then electromagnetism is about, you know, 100 times weaker in some fundamental measure than the strong nuclear force. That's why, you know, big atoms don't fly apart. It's because the strong nuclear force binds the protons together more than the electromagnetic force pushes them apart, right? The weak nuclear force is kind of a strange one that we, you know, results in kind of stranger phenomenon like nuclear decay. And then gravity, if we think about, for example, the comparison of the gravitational force to the electrostatic force in a hydrogen atom, well, there's about 40 orders of magnitude of difference between those 2 forces, right? And in other words, the electrostatic force is 10 to the 40 times stronger than gravity. And furthermore, these top 3 are pretty successfully described by the standard model, or quantum mechanics, right? What we call the standard model, which is based on quantum mechanics, whereas gravity is a kind of a classical field theory, right? And so these 2 models of how nature works are actually quite different, right? Quantum mechanics is probabilistic, and, you know, classical mechanics is completely deterministic. And so there's kind of 2 things going on here. We have these 2 different types of models of nature that really describe almost different universes in the way they work, quantum versus classical theory, and then this huge discrepancy in strength. And whenever we see something, such a huge discrepancy in nature, right, between this and this, then we want to ask the question, why is that? Is it just by chance, or is there something fundamental going on that gives us a reason why gravity is so weak compared to the other fundamental forces, right? And so one major goal of particle physics is to kind of, can we find a framework that explains all of these forces consistently, right? That isn't quantum versus classical, but is there a framework where we can kind of describe everything consistently, a mathematical framework? And also maybe we can answer the question of why is gravity so weak, right? Compared to, and you might think, well, gravity is strong, right? On the everyday experience, that's what we feel the most. But, you know, I encourage you right now to pick something up and lift it up over your head. And by using a quantity of electromagnetic stuff in the muscles in your arm, you've overpowered the gravity of the entire Earth pretty easily, right? So there's just one example of how gravity, at least compared to electromagnetism, is pretty weak, right? We can easily overpower it in kind of with the amount of stuff we have in our muscles, right? Okay. And so that's not the whole story. Well, just to kind of summarize, so gravity is one of the 4 known fundamental interactions. We know it holds us to the Earth, and we know it's responsible for orbits. And in physics, we're often looking for unifications, right? And I just, previously, just a second ago, I said we wanted to unify these 4, one goal of physics is to unify these 4 interactions, these 4 forces in a consistent framework. And one of the first examples of kind of unification of things that were seemingly distinct was actually from Newton. And Newton kind of brought together the ideas of what is causing things to fall on the surface of the Earth, and what if that was the same as what is holding the planets in orbit around the Earth. Now, back in these times, it wasn't necessarily thought that what holds us, what happens terrestrially on the ground is necessarily the same, that that's not necessarily the same forces that are acting celestially or in the heavens, right? But Newton was able to say, okay, well, what if these 2 phenomena were actually part of the same thing? And by doing so, that led to the formulation of the universal law of gravitation, right? Where r is the distance between masses m1 and m2, and g is just a constant that turns those quantities into units of newtons or force, right? And so so that was a kind of a first example of one of these kind of unifications, right, that we have in physics. And we're kind of still searching for more of them. Okay. Of course, the inverse square law then directly leads to elliptical orbits, and we was able to agree with measurements that were made. And incidentally, it also predicts that all objects accelerate in a gravitational field at a uniform rate. And that actually turns out to be something that has a much more deep significance, right? So fast forward, Newton's law was pretty much the name of the game in gravity for about 250 years. But at the time of Einstein and in the late 1800s, new model, people were working a lot with light, for example, and there was a lot of new experimentation going on. And it was deeply troubling to Einstein. For example, when you think about special relativity, right? And you look back at this law, well, in special relativity, distances are measured, the amount of distance you measure depends on the reference frame, right? Depends upon your velocity, for example, due to length contraction. And also, this force in this law seems to be transmitted instantaneously between masses m1 and m2. So both of those things troubled Einstein, because you could ask the question, well, who measures the distance r in that force law? And how does it get transmitted between the information about the force being, how is that transmitted faster than the speed of light? Those things seem inconsistent with special relativity, right? In other words, if I jiggle a mass on the Earth, does its gravitational effect on something across the universe happen instantaneously? And special relativity says it can't. But that was not really in Newton's law at all. So this kind of led Einstein down the path to formulating general relativity, which is our current best model of gravity, right? And it relies on the fact it basically leads to the idea that gravity is just really a curvature of a 4-dimensional space-time, and objects within this curvature are just kind of following their natural path through space-time, right? It's kind of like if the sun was a bowling ball on a mattress, you put a marble nearby, and it's just going to follow around, not just because of the way the mattress is deformed, right? And so that leads to something very fundamental to general relativity, which is the idea of the equivalence principle. And so the equivalence principle says it doesn't matter what kind of marble we put on the mattress, whether it's a wooden marble, a lead marble, a copper marble, a glass marble, whatever we put on here has no choice but to just follow the curvature of space-time, no matter what it's made of. And I hope that makes sense. If it doesn't, let me know. But if and that idea that the composition of an object does not affect its gravitational force is really tied to the geometric nature of gravity, and gravity being this kind of curvature of space-time, right? It also implies that the 1 over r squared form of Newton's law has also a deeper significance. It basically reflects Gauss's law in a three-dimensional space. So in other words, the 2 that we have in the exponent of r is really tied to the three-dimensionality of space. So if you happen to live in a universe with 4 dimensions, that would be a 1 over r cubed. And if you happen to live in a universe with 5 dimensions, it'd be 1 over r to the 4th, right? And so on and so forth. And this theory, this geometric theory of gravity, general relativity, has been super successful. And basically it's passed every test that anybody has ever put it to for the last 110 years. They're looking at how the planets move around the sun, the deflection of light around massive objects to create gravitational lenses. Finally, the observation of gravitational waves, within the last 10 years. And nothing that's been discovered has been inconsistent with the predictions of GR, general relativity, so far. Okay. So it's very successful, but there's still a lot of things that we don't know. General relativity works seemingly really well, but as I mentioned, it is fundamentally inconsistent with the quantum mechanical nature of the standard model, right? And so one idea to kind of unify the classical and quantum realms is string theory. And again, that's just one possible idea. You may have heard of string theory. And string theory naturally requires extra dimensions of space, just in the way its mathematics works, okay? And so that may be an option. And another question what we want to ask is, why is gravity so weak compared to the other fundamental forces? Is there something going on there that is that relative weakness hiding some other fundamental fact, okay? This is called the hierarchy or naturalness problem. In a particle physics context, for you particle physicists out there, it's the same as asking the question, why is the Planck mass so much greater than the electroweak scale? There's many orders of magnitude there. Why is the electromagnetic force 10 to the 40 times greater than the gravity in the hydrogen atom? And string theory, one idea from string theory is that, well, maybe because gravity is a geometric theory, maybe it's really just as strong as the other fundamental forces, but its strength is diluted or spread out through the extra dimensions that string theory requires. This was an idea that came about, string theory or M theory. This was an idea that came about kind of in the late 1990s, about when I was in grad school, and that led to my kind of PhD work and from there. And so, I already mentioned that the 2 in Newton's inverse square law, the 1 over r squared, is tied to the 3 dimensions of space. So if now string theory is saying there are extra dimensions of space, maybe that 1 over r squared law doesn't work at certain distance scales, okay? And there's a whole other bunch of kind of troubling astronomical things, not to mention some particle physics things that I won't get into, but, what is dark matter? There seems to be an excess of gravitating matter in the universe that we don't really know what it is. We call it dark because we don't know what it is, and it doesn't really interact with electromagnetically. It doesn't interact with light. And is there an unknown property of gravity or something else that is causing the universe's expansion to accelerate, which is something we observe? And again, that's maybe that's some new phenomenon that we don't understand, or maybe it's a flaw in our understanding of gravity itself. Okay, so there's a whole bunch of kind of fundamental questions that surround gravity, um, and reasons to try to incorporate it with quantum mechanics, right? And so anyway, that's kind of what we don't know. And I just want to talk kind of for the rest of the time today about what we can do in the lab. Okay, and I'm not going to be talking about high energy experiments that require a lot of equipment and huge devices. Those of course are great and they have their place and they can probe similar questions, but I'm going to be more focused on what we can build in the lab and kind of how some students have been contributing to that over the years. So the first kind of thing we'll look at is this part of Newton's law, which is the force inverse square for all values of r, right? And it turns out we know the inverse square law works very well for planetary distances, right? Like the distance between the Earth and the Sun, even for over Earth-sized distances. And it turns out in the laboratory, gravity has been very well tested. In other words, we've tested that this is in fact a 2, down to, sub-millimeter distances. So we bring mass 1 and mass 2. Basically, we want to ask how close can we bring mass 1 and mass 2 together and still say that this is a 2, right? String theory, it turns out, predicts that there might be reasons that it's not a 2. Like I mentioned, there might be extra dimensions of space. And those extra dimensions, it turns out, up until about 1999, nobody had ever even measured that gravity exists between masses that were separated by a millimeter. Okay. Again, because it's very weak compared to the other fundamental forces. And so there was various theories in the late, in the 20, 30 years ago that were like, whoa, well, gravity's never even been tested at the millimeter scale. Maybe these extra dimensions could be kind of curled up, like, and they could be as big as a millimeter. It's kind of like, imagine a tightrope walker and they can walk across the tightrope, right? And that'd be like one of our normal dimensions of space. But if you're an ant, you can walk in that direction, but you could also walk around the tightrope. And that would be kind of one of the curled up dimensions of string theory. So I'm not a theorist and I'm not going to get too into it. But basically, the ideas were that there could be compact extra dimensions of space, and we would have never known about them because only gravity is able to test them. Okay. And the rest of the other fundamental forces are kind of stuck on the three-dimensional space that we are familiar with. There's also some various theoretical scenarios. People kind of threw some fundamental constants together and said, oh, that turns out to be a distance of around 0.1 millimeters, and maybe there's some significance to that. And models were proposed to try to, has to do with the observed amount of dark energy in the universe. And maybe people were like, oh, well, maybe there's some new interaction that could be observable when you bring things close together on that scale. And then there's a whole other host of ideas out there from particle physics and other venues as to, the question of, are there other forces? And if there are forces of nature that we haven't detected because they're weak, maybe they're mediated by exotic, weird particles. And maybe some of those particles could be dark matter candidates, right? Or solve the strong CP problem, if you're familiar with that. Anyway, so there's a lot of reasons to test gravity and bring masses close together from a theoretical standpoint. Okay. And now I have to get a little bit into a little math. Okay. And if you've studied, first year physics gravity, right? Remember the force goes as the inverse square, gmm over r squared. If we write down the potential energy between two masses, m1 and m2, it would look like this first term out here, right? This is the gravitational potential energy between 2 point masses, m1 and m2, right? And the way we typically model some kind of deviation from that, or some kind of basically something being wrong with relativity, is we add this term, or something being wrong with general relativity, or some new effect happening at a short distance, is that we add this term over here that we call the Yukawa term. And the Yukawa term just has a dimensionless parameter alpha and a range lambda. And so when we test the inverse square law, we're basically asking the question, is alpha 0 within the measurement uncertainty for a given value of lambda? Okay, so I hope that makes sense. And so if this is the normal potential energy that falls off with distance like we expect from Newton, and this is something that falls off faster than Newton. And so it acts over a shorter range. And so the range of the interaction is kind of given by this parameter lambda. And the strength relative to regular gravity is given by alpha. Maybe I'll stop there for one quick second and make sure there's no questions on that. Okay. There's various ways you could parameterize some deviation from Newtonian behavior, but this is just one way that's become kind of standard in the field. Okay. What we see here is a plot of the strength alpha versus the range lambda. And this is so a 1 on the vertical axis here would mean some new effect that is as strong as gravity. And the x-axis here is just in meters, right? And so we have all the way at this end, we have a centimeter, right? So that's where, we're familiar with centimeters, or maybe it's a millimeter over here on the left-hand side. I think the centimeters here. Here's a meter. And then here we have all the way up to huge distances, like the distances between the planets. So it's a logarithmic scale, right? And there's been various measurements that have been done to try to measure if alpha exists or if it's non-zero, right? And so these measurements can put kind of an upper limit on alpha. And so everywhere in yellow here, basically we can say that alpha can't be that big, okay? Alpha can't be that big. So this yellow region has been excluded by experiments. And this was the situation about 25 years ago. And it turns out that, again, nobody had really even measured the fact that, nobody had even measured anything of gravitational strength at the millimeter scales, or way over on the upper left-hand part of this plot, okay? So if you want to measure gravity better and better, you keep doing experiments that go for higher sensitivity, which means coming down, or at shorter distances, which means going left, right? And so new experiments will kind of carve out more pieces of this parameter space to search for if this value of alpha is 0 or not, okay? Or, what kind of limit can we put on alpha? And you can see this is lunar laser ranging, has put really stringent limits on alpha can't be bigger than 10 to the minus 10 at Earth-Moon distances, okay? So it's got to be a very small fraction of the gravitational force. Up here, kind of on the Earth side, Earth scale distances, we can only say that these, this could be as big as 10 to the minus 3 or something like that, and we wouldn't have the sensitivity to say otherwise, okay? And again, up until about the year 2000, 2001, we didn't even know if gravity existed between things separated by a millimeter. Kind of wild to think about, but true. Okay. How do we do it? Well, pretty much the same technique that's been going on for about 300 years. It's called a torsion pendulum. We have a very thin fiber, and from it, this is a kind of a simplified version, but this is the way Cavendish first measured, for example, big G back in the late 1700s. We bring two masses close together, separated by some distance r. Newton's law of gravity says there'll be a force of attraction between these two, and therefore our pendulum will twist, right? So this is a pendulum that, not like a regular simple pendulum, but it's a pendulum that twists. It hangs vertically and twists about the vertical axis, right? And that's kind of a simplified version of the torsion pendulum. This is the pendulum that has been used by the University of Washington group to make the most precise measurement or the shortest distance measurement of gravity to date. And you can see if I compare this and this, they look quite a bit different, right? And that's because the technology has improved over the last couple hundred years. And, we have a more complicated mass distribution. And instead of hanging this, so the holes and are actually kind of like the dumbbell masses from the last slide. And then this mass distribution down below is kind of like the M2 up here that we would kind of move back and forth. Instead of moving it back and forth, we move it around. The details aren't super important, but just kind of the visual image of we're still using a torsion pendulum, but it's become a lot more high tech, I guess, in the last couple hundred years. And so this pendulum, which actually this is an actual picture of it from my friend Dan Kapner, who worked on the experiment. These are some pictures of it. And this is, this is the instrument that has made the smallest distance measurement of gravity to date. And we can say that the inverse square law seems to hold down for masses that are separated by 39 micrometers or bigger. Now, that sounds kind of small, but if you think about it, a human hair, that's about the diameter of a human hair, roughly speaking. And so it's small, but it's not like immeasurably small. It's not so small that we can't imagine it. And so there's still room to do tests at shorter and shorter distances. Basically this also kind of excludes the extra dimensions of string theory have to be kind of smaller than this distance, in some sense as well. Although there's various versions of that, but anyway. So that is not an experiment I've worked on, but that kind of shows you the kind of some of the state of the art. Okay. Well, I think I did actually as a postdoc work on this part, but anyway, it was a long time ago.
I think we have a question.
Yeah.
Have they ever done this in space, like on the ISS or something?
Have they ever?
Yeah, I heard that. Yeah, it turns out in space you can't really make a torsion pendulum that well, right? The beauty of the torsion pendulum is it always hangs vertically, and so it only is sensitive to horizontal components of gravitation, right? So the torsion pendulum makes us insensitive to the Earth's gravity, right? So you could do similar experiments in space, but they would have to be different. They couldn't be torsion pendulums. There's something called Gravity Probe B, which has been done some very precision measurements of gravity from space, but not at short distances like this. Does that make sense or no?
And of course, Gravity Probe B also was not able to measure the one thing that was more interesting, and they were able to measure the thing that was less interesting.
Exactly. Yeah. I think anytime you put things in,
Just overruns and took like 40 years.
yeah, right. And anytime you put things in space, the cost just goes up incredibly high, and you kind of run into all kinds of other things. So there are proposals to do these kinds of measurements in space, but nobody's ever really done it yet, at least kind of with the level of sensitivity that we're talking about. Yeah, good question. Thanks. Happy to take questions as we go through. So now remember this plot here. We're going to zoom into the red arrow, the red circle, right? And in the red circle part, if we zoom in, we can look at shorter distances. So now this is like maybe, I think, this is 10 micrometers here. And so the right side is a centimeter, right? And now the left side is some number of micrometers. And if we think about it, in this parameterization, a value of alpha being 1 means it's a deviation with the same strength of gravity. And 1 is 10 to the 0, right? And so if these experiments can measure at the level of alpha equals 1, that means they can measure gravitational strength forces. And so the pendulum I just showed you was able to measure gravitational strength forces if we drop down at 39 micrometers, okay? And this just shows you the variety of different experiments that have been going on. They're all some version of a torsion pendulum down here, at least the ones on this plot. There are other people doing really cool things with optically levitated masses and precision force micro oscillators and things. And those all do really well, but they kind of do really well kind of up here, kind of off this plot. And they don't really have the sensitivity yet to actually measure gravitational strength forces. And at Humboldt, we've been working on for quite a number of years an experiment. And don't worry about the two different lines, but basically our goal is to try to get to this blue dashed line to do kind of a yet slightly improved measurement of gravity in the kind of 10 microns to 1 centimeter distance scale. Okay. And how we're going to do that, anyway, that's where we hope to get. And how we're going to, so that's one thing we're going to try to, I'll show you with the experiment here in a minute. Another part of this is testing the equivalence principle. Does the type of mass matter? And this means, like, does it matter whether we make masses out of, different materials have different numbers of protons and neutrons per unit mass, for example. They have different numbers of, remember, baryons are like 3 quark particles, and leptons are like electrons, like fundamental particles. So you can have the same amount of mass, but it can be made of different fundamental things with fundamentally different quantum numbers, like baryon number, lepton number, things like that. So the question is, does the type of mass matter? In Newton's law, it doesn't. And in general relativity, it doesn't. General relativity says all masses should accelerate equally. If that wasn't true, then either there's something wrong with our model of gravity, or there could be new forces of nature that depend on these other types of quantities, like the number of protons or the number of neutrons or so on and so forth, right? And so another goal is to test what's called the weak equivalence principle of general relativity. And that's just kind of like, do the rock and the feather hit the moon's surface at the same time, right? Or the hammer and the feather or whatever. Do things fall equivalently in a gravitational field? And so that's another thing we test. We test that. We're looking to test, does this weak equivalence principle hold over short distance scales? Nobody's ever done that measurement before, at least in a dedicated sense. And if it doesn't hold over if things don't fall the same way over very short distances, is there some new force of nature that is responsible for that? Or is there something wrong with gravity? Is it dark matter particles? Blah, 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 right? There's a whole, as an experimentalist, we're going to go in and see what we find. And then we'd have to do, if we saw something weird, we'd have to do more experiments to figure out what was causing the anomaly, okay? Just real quick, in a quantum mechanical sense, the potential energy, we're talking about kind of like an interaction between two objects with quantum charges Q1 and Q2. And so it looks a lot like a gravitational potential energy, but it acts over a short distance, and it couples to some other property of the materials that is not mass, right? This is kind of this potential energy, this general form. If the Q's are just mass and the range is infinite, then you get something that looks like gravity, right? But here, these Q's would be some other properties of the materials that are not mass, and the range could be whatever. We don't know. Okay. And so, again, if these forces do exist, they could be mediated by weird new particles. They could be due to all kinds of things that particle physicists like to study. Okay. And what's interesting is that most ideas that try to unify general relativity and quantum mechanics predict that there will be effects that violate the equivalence principle, that cause things to fall differently in a gravitational field. Again, this is another type of one of these plots, but the only point I want to make here is that the left-hand side is a centimeter, and tests of the equivalence principle are really, really good. It's actually one of the most precisely tested things in all of nature when things are far apart. Like we can really say that the Earth and the Moon fall the same way towards the sun. That's really, even though they're kind of made of different stuff. But down at the centimeter scale and below, there's really been no dedicated test of the equivalence principle. So that's another thing we try to do at Humboldt. How do we do it? We have a torsion pendulum that looks kind of like this, and we oscillate it. We have an attractor mass nearby. This is a former student, Holly, working on that a long time ago. We measure the twist of our torsion pendulum with a laser autocollimator that bounces a beam off the pendulum. This is all in ultra-high vacuum or high vacuum. And this is just a little blow up of our apparatus. Here's our fiber that holds our pendulum, and we have an attractor mass nearby. Now what we do is we shake this mass back and forth, and we look for the pendulum to respond. And the pendulum is made of titanium and aluminum, and the geometry is in such a way that if Newtonian gravity is all there really is, then the pendulum won't twist much at all. Okay. And so but if there's a short range interaction, that short range interaction will be different because titanium on this side is closer to copper and aluminum on that side is closer to copper. Okay. So that's the idea. So we can basically ask the question, does the inverse square law work? And also, since we have titanium and aluminum, if the interaction is only over a short range, we can actually see if titanium and aluminum fall toward copper equivalently. So that's kind of the idea. We do two tests in one. We can do the inverse square law and the equivalence principle. We've gotten some data. If you've ever seen if you ever studied oscillators, you know that our simple harmonic oscillator has a well-defined frequency. And so this is some data we took that shows this is just the free resonance of our torsion pendulum. It's very slow physics. The pendulum has a natural period of about 5 minutes or 300 seconds.
I have another question.
Okay, real quick, I'll just say what this peak is. And this is the torque that we've imparted to our pendulum by modulating our attractor mass. So we see that we can see it. Okay, yeah, go ahead.
For the pendulum components, are the titanium and aluminum the same mass or the same?
They are.
Okay.
They are, and that gives us that helps us be insensitive to the Newtonian signal, the regular signal. Imagine if this was an infinite plane. Imagine doing Gauss's law. If this was an infinite plane, it wouldn't matter where it is. The net force on the pendulum and the net torque on it would be the same, right? And so we kind of use the infinite plane approximation a little bit to help us out here as well, right? Because an infinite plane makes a uniform field. So anyway, at Humboldt, we've done some measurements back in 2022, and we've been working on things a lot since then, and we were able to kind of get to this level of sensitivity compared to other experiments, and this is our eventual goal. So we're working on it. And it's because it's hard. Everything is stronger than gravity. You have electrostatic interactions, which we have to shield out with a conducting membrane. We have magnetic impurities. Our building rocks around over the course of a day. You have to get basically we have to get our pendulum and attractor masses to within tens of microns of each other, which is hard. Seismic noise is a problem, although as I say, we do very slow measurements, and so we're not really sensitive to vibrations that much. But we are sensitive to things like temperature fluctuations, the building tilt. Just as an example of that, our building, if you measure its tilt over the course of a day, the building follows this blue curve. This is in days. So you can definitely see a day, night, day, night, day, night, and that's because the building just heats up and cools down. And since a torsion pendulum always hangs vertically, this is a problem because it means if it's always hanging vertically, things around it are moving around. And it turns out to be at such a level that we care about. It's like tens of micrometers, which is kind of the same size distances we worry about. And so some students built a real simple feedback loop based on a resistor that heated up the legs of the apparatus to thermally expand them. And we were able to kind of implement a tilt control system that keeps our apparatus flat really well over the long periods. And that's, again, with a resistor and a LabVIEW feedback loop. So kind of cool. Also, the level of angles that we have to measure. I gave a talk in Boston once, and if you imagine a penny which we still have pennies for a while. But if you imagine a penny in California as viewed from Boston, that's the level of angle we need to measure in order to look for violations of Newtonian gravity with our system. And that's a nanoradian. And so we needed to build an optical system to measure small changes in our pendulum's twist angle. And a student designed and built that too. You can't buy that level of, well, you can maybe for like $50,000. But anyway, a student built a nice optical system to do that. And it works. Just some pictures of students in our lab. Here's a torsion fiber. Here's our pendulum before we assembled it together and gold coated it. Yeah, so it's been a long process of getting this up and running, but it works pretty well. I'll skip over this real quick. I have a collaboration with the University of Naples in Italy, where we're kind of to do a similar thing, except we're using liquid mercury as the mass that pulls on the pendulum. And so we fill up these blue tanks and empty them with mercury, fill them up, empty them, and then we look for the effect on our pendulum. So that's something that I've been working with for the last few years. Similar experiment, testing the same things, kind of slightly different idea, reusing some hardware from Lisa Pathfinder. I have a couple slides on our big G measurement. Big G was kind of inferred from Cavendish's measurement, in 1798. It turns out that value is still within 1% of the modern value. And the precision of big G has only improved about 1 order of magnitude per century, which is not great from a fundamental measurements kind of point of view. And even worse, these are measurements from the year 2000 up until 2018. And these are all measurements of big G. And that looks terrible, right? I mean, these are the measurements in their error bars. And even the 2 most recent measurements of big G made by the same group disagree by many, many, many error bars. And so this is the worst known fundamental constant. And it's a problem. It's a kind of embarrassing, first of all, but it's also a problem because we don't really know what G is. And even the last 2 measurements by the Chinese group in Wuhan don't agree, even though it's the same people doing the measurements. 2 different techniques, but same group. These experiments have had a lot of technological improvements. This is the first kind of modern big G experiment with a torsion pendulum done in Washington in 2000. I was a grad student then. I took that picture of it back then. It was able to measure G to 14 parts per million. And then in 2018, the Wuhan group was able to make 2 independent measurements at the 12 part per million level. But again, those disagreed with each other. And so there's an international agency that sets what the values and uncertainties of the fundamental constants are. And it's true that from 2014 to 2018, this is the uncertainty. The uncertainty went down a little bit from 31 to 15 parts per million. So that's good. But actually, the value of the codata value of G in 2010 actually had a larger uncertainty than in 2006 because of all these measurements that didn't agree with one another. And so I'm involved also with a collaboration where we're building an experiment in Indiana University, Indianapolis, which is a scaled up torsion pendulum test of big G, where we can use 2 different techniques in the same apparatus. So not only are we going to try to measure G at the 2 part per million level, but we're going to try to do it 2 different ways in the exact same apparatus, which might help us understand why some of these previous experiments are in disagreement. And this experiment is being built. There's Professor Decca under 2 tons of granite when we were trying to get this thing assembled. And it's slowly coming together. One of our undergraduates from Cal Poly Humboldt, M. Ord, is now the PhD student in Indianapolis working on this project. And we're about ready to take some data soon. And so hopefully we'll be able to measure G at the 2 parts per million level. But it's a big problem. We don't know what G is, and well, we don't know it very well. And even worse, all of these measurements disagree. Okay. Last thing I'll touch on, I'm kind of cruising through a lot of pretty cool stuff, is that we just got a grant to start developing novel quantum sensors in collaboration with Holly Leopardi, who's at NASA Goddard Space Flight Center. Holly was also a student of ours. She graduated in 2014, got her PhD in Boulder, and now she runs the Quantum Engineering and Sensing Technology Laboratory at Goddard, and she's also the USA, one of the scientific leaders for the USA, the United States contribution to LISA. She just became that position, the laser interferometer space antenna for gravity wave measurements. So anyway, Holly was one of our students. This was when we went to a conference in 2011, and this was just in December when I visited her Quest lab out in Goddard. And the idea is that she uses cold atom interferometry and novel atomic clocks to build devices to measure small variations in gravitational fields. And these devices will eventually be flown in space, such as the atom interferometer gravity gradiometer and a spaceflight compatible optical strontium clock. And all of these things could be used to map the mass distribution of the Earth and how it changes, or to do also fundamental physics tests like I was talking about. Or actually, there's other applications to spacecraft navigation and things like that. So we just got started with that in September, and a couple of students are going to head out to Goddard over the summer, assuming grants don't get canceled and things, but head out to Goddard over the summer and work in Holly's lab. And we're building a setup at Humboldt to do some kind of spectroscopic type measurements that to train the students in that, so that when they get to Goddard, they'll be ready to work in Holly's lab. So long story short, there's a lot of unanswered questions in gravitational physics still. There's a lot of precision measurements that remain to be done. Big G is really a mystery why all of the measurements scatter around so much. And in addition to these kind of standard classical ways of measuring gravity, there are going to be a lot of new techniques in atom interferometry and quantum sensing. And I think you're going to hear about more of those when you hear about from Giorgio Gratta later this semester. So anyway, yeah, more pictures of recent students at conferences, and I'm happy to take any questions. And sorry, that was a lot there, but anyway, thanks.
Thank you very much.
Yeah.
Let's see if we have any more questions. I remember Holly, because
You
she
do?
at the Far West meeting.
Yeah, she went to a couple of those back in, it's probably 2012, 2013. Yeah.
That's about right.
Yeah, and so
That's really cool that she's a Goddard. I had no idea. I'll have to visit her the next time I go there.
yeah, and she yeah, just in January or December became the scientific, I can't remember the exact title, but it's something like the scientific program lead for LISA in the US. So yeah.
I think the actual program scientist is Ann Hirschmeyer.
Yeah, yeah, and then there's Ira Thorpe too, right? Anyway, I can't remember her exact title, but she's in charge of something with Lisa now. So yeah.
That was super interesting, because I had no idea that G was so poorly known. For example, I knew about torsion pendulums, I knew about the millimeters and everything, but I did not know.
Yeah, and it's gotten worse really in the last 20 years, because the measurements have gotten better, but they disagree more, right? So
They're like the Hubble constant.
yeah, right, exactly. So
It's sort of like the sun, every time you get more data on something and you have this great theory that explains it, and you get more data and it just blows it to bits.
right. Like the solar neutrino problem too, right? Yeah.
Solar neutrino problem, also how the corona, what powers the corona.
Right. So
Perennial problem that is solved almost every year by somebody and then unsolved the next year.
right.
So we have any more questions from anybody? How about from anybody online, I can unmute you, all you online people. Or you could like raise your hand or something,
Yeah.
question, I could unmute you at that point. I don't see any hands being raised.
Well, yeah, you're always welcome to email me or, reach out to. I'm happy to answer questions like that as well. So,
Yeah, and so you got some grant money from Mosaics. That's the one NASA program I thought might be in trouble. But so far,
I still am wondering about it, to be honest.
nobody that I know with NASA money has gotten any kind of stop work order, and we've all been told that nothing that we do is DEI, and we should all keep calm and keep working.
Yeah, I've just been kind of, well, been trying to spend the money that I have. And then, yeah, just kind of keep going. And yeah, we did get a Mosaics grant. So we're pretty excited about that for
I mean,
sure.
I didn't apply, obviously, because I've had too much NASA money, plus I was on the committee that wrote the proposal call.
Oh yeah, did you work with, there was a study committee too. Did you work with Regina Jorgensen at all on that?
Maybe. It
She's
was,
going to be our new faculty member starting in August. So, but she was on the pilot on the working group study for Mosaics, I think. So
was on they had a bunch of different groups, and I was leading one of them, but I forget which one it was now. That was
yeah.
Bridges, and then they renamed it, and
Yeah.
they seem like they're putting out another call, so it hasn't been stopped yet.
I know. Yeah, it's pretty exciting. And then, yeah, Holly was actually the one, because we've remained friends over the years, and she, like summer of 2023, she saw it, and yeah, and she's like, we should do this. So I was like, okay, yeah, it worked out. Yeah,
Yeah.
that's cool. But
Okay, no more questions from anybody here. I don't see any raised hands, so I guess we'll just thank you very much.
well,
And
thanks so much, Lynn, and all the best. I'm sorry I couldn't make it down.